Let's have a quick short lesson on the inscribed angle theorem on which our first assignment was based. So there is a possibility that some of you haven't seen this beautiful simple proof of one of the most nicest result that we learn in high school. So the inscribed angle theorem says that if you take the center of the circle and take the chord AB, then any angle subtended by this chord or arc in the circle is going to be half of this central angle, which we shall call as theta. So what we're really trying to say is that you take D anywhere on this part of the circle. You can take the point D anywhere on this part of the circle, and all the angles subtended by the chord, which is basically joining A to D to this B, so this angle is going to be theta by 2. And it doesn't matter now where you take D, all these angles are going to be theta by 2. So it is definitely a very good looking and pretty theorem, and the inscribed angle theorem leads to several nice beautiful results in geometry, which we shall study very soon. Now, how are we going to prove that all of these angles are theta by 2? Now the proof will be in 3 steps, and that is why this theorem is worth talking about, because breaking down the problem into the simplest case followed by 2 other cases is a classic illustration of how you tackle the simple case, and that will help you to break down the difficult cases. So what is the simple case here? The simple case here is that you extend AC and along the diameter and take the point D on the diameter extended by the radius AC, and now there is a symmetric point on this side by extending the radius BC. Now both these points, I'm just going to call them as D1, are going, because that's the first case, is going to be extremely simple to show that A D1B is theta by 2. So this is the first part of the proof, where we prove that A D1B is theta by 2, as if the central angle is theta. So we'll do this as the first case. Now this case helps us to prove the second case. The second case is where D can lie anywhere on this green arc, and for example, I'm just going to call it D2. I'll just call it D2. So anywhere on the green arc, we can now prove that this angle is theta by 2. Now this one will be easy after the first case. Now that still leaves us a third case. If the point lies along the blue arc that I'm showing you here, and I'll just call it D3. Now there is a symmetric part here, the blue arc on this side. Let me just call it D3. Okay, so D3 and D2 will be easy after we do D1, and D1 is really going to be easy, and so let me do D1 now. So I have the circle, and I'm going to try and prove that if this angle is theta, then this angle is going to be theta by 2. So this angle, where this is, I'm going to call it as D1, and this angle is what we are gunning for. Angle A D1B is equal to theta by 2, and I will write this to prove that. Alright, let's get down to the proof now. Notice that CD1 is equal to CB, because both are radius, and that's the first simple observation, and that would mean that CD1 is equal to CB. So I've just shown that these two sides are equal. Now if you consider triangle BCD1, I'm basically referring to this triangle. Now this is clearly a isosceles triangle, so is isosceles. So now that would immediately mean that the base angles here are equal. I'll just call it Y. So the base angles of this isosceles triangle are equal, and now notice that this angle theta, is an external angle. So theta is equal to y plus y, because it's an external angle to the triangle. This is a famous simple external angle theorem, and that would mean that this is equal to 2y, and this immediately gives us that y is equal to theta by 2, and we're done with this proof. So it was very nice, very simple. Now this simple idea is going to be repeatedly used to handle the next case, which is that if the point D is now in the green part. Now what's the green part here? So just to repeat, this was D1 and this was D1, and both of them were very easy to handle, the symmetric case. Let me just continue the labels here, C, A, B. And now what we are saying is, if you look at the green part of the arc, now this is going to be easy to handle. Let's say that the point D2 is on the green part, and what we are trying to prove is A D2B. We're trying to prove that this angle is theta by 2, if this angle is theta. So to prove that angle A D2B is equal to theta by 2. Now it's very simple once you have a construction line. So the construction line is from D2 to the center of the circle to the end of the circle. Now once you draw this construction line, you can see that if this angle is y, then this angle is equal to 2y. Now that is because we have this particular triangle is isosceles by pretty much the same reason we've given before. Now if it's an isosceles triangle, then if this is y, then this is also y, and therefore the external angle here will be 2y. Now same idea repeated. If this angle is x, if this angle is x, then this angle is going to be 2x. So now from the figure, ACB is equal to 2x plus 2y, that is 2 times x plus y, and angle AD2B is equal to, if you look at the figure, x plus y, and I think we are done. This would clearly mean that angle AD2B is equal to half of angle ACB, that is equal to half of theta. So that ends the proof. Now what I shall do is, I shall not drag this lesson too much. You can use the absolutely same idea to show that if D3 lies on this part of the arc or this part of the arc, so let me just call it D3 and D3, you should be able to carry home the same idea and prove that angle AD3B is also equal to theta by 2. I think you know what the first step is. The first step is to draw a construction line, just like we did this for the previous one. I just leave you at that because the figure is already looking terrible. So I shall just join D3 to C, saying that please use the construction line and use a similar idea to also prove that A D3B is equal to theta by 2, and I shall leave this as homework for you, and that would help me to bring this lesson to a quick end. Thank you very much, and please do have a look at this if